this video, we're going to be doing some counting exploration, not just counting 1, 2, 3, but different ways we can do things. And then we'll also take some notes on how we can find out how many options there are for things. All right, so number 1, we have 3 students. We have Andy, Beth, and Kara. They must arrange their desks in a row in their classroom. Your job is to figure out how many different arrangements they can make. Make a list of all possible arrangements. How many arrangements are possible? So I called them Andy, Beth, and Kara so we could label them as A, B, and C. So our first arrangement, if we were to line them up in a row, would just be to call them A, B, C. Well, what if Kara and Beth trade places? Then they're A, C, B. Well, what if Beth comes first instead? And we can have Beth, Andy, Kara, or Beth could come first, and then we could have Kara and Andy. Or Kara could sit first, and then Andy and Beth. Or Kara could sit first, and then Beth and Andy. In these, if we're making a seating arrangement, it matters what order the letters come in. Each of these are a different choice, and we have a total of 6 possibilities. The other way we could have figured this out algebraically is we have 3 seats. How many ways can I choose the person who sits down first? There's 3 ways to choose the first person because we have 3 people, Andy, Beth, and Kara. Once we get to the second desk, we only have 2 people left because we've already chosen one. So there's 2 people to arrange in the second desk. And then by the time we get to the third desk, there's really no more choice involved. There's only 1 person left who's going to have to sit there. If I do 3 times 2 times 1, that equals 6, and this is how I could find this algebraically without listing out all of my choices. All right, this is nice because when we get to number 2, it says Dana is added to the group of students in number 1 above. So now you have to arrange 4 students in a row. How many arrangements are possible? Well, if I had to use this method where I start listing them all out, A, B, C, D, A, B, D, C, A, B, no, can't do that one yet. A, D, B, C. Inevitably, what happens is we lose count of how many of these arrangements we've done, and we need to come up with a mathematical way to do it. But again, if we have 4 desks, we just need to choose how many ways are there to put a person in each desk, and then multiply those together. So there's 4 students we could choose for the first desk, then 3 are left in the second desk, 2 for the third desk, and by the time you get to the 4th choice, there's no more decision making. You have to put the student there. So 4 times 3 times 2 times 1, I'm going to use my calculator. 4 times 3 times 2 times 1 is 24, and I have 24 ways that I can arrange 4 people in a row. All right, let's scroll down here to number 3. In number 3, we have Mr. Smith's class. It says Mr. Smith's class wants to elect a president, a vice president, and a treasurer. The names of students in his class are Arlene, Bud, Kathy, David, Eli, Fred, George, Harry, Isaiah, Jack, Kim, Larry, Marlon, Ned, Oprah, Perry, Quentin, Ralph, and Sarah. Okay, that's a lot of kids. If we listed them out, we could count them. There are 19 students in there. How many different slates of offices are possible? So in this case, it's kind of like the desks. We're choosing 3, and it matters the order we pick them because one is going to be a president, the next one's going to be a vice president, and the third one's going to be a treasurer. So it's just like sitting in a desk. It matters who gets put in the first spot versus the second spot versus the third spot. So just like I did before, I'm going to multiply them together. In the examples above, I used everybody. In this one, out of the 19 students, not all of them are going to get chosen. But regardless, I have 19 ways I can choose my president. Once I've chosen the president, then I only have 18 people left that I could choose for vice president. Once I've chosen my vice president, I only have 17 people left that I could choose for treasurer. So I have 19 times 18 times 17 is 5,814 ways that I can elect 3 different officers in my class of 19 students. So that's a big number. There's a lot of different ways that we can choose these. If we had to list these out, it would be way too many. All right, Number 4, Mr. Smith's class, so the same one above, we still have 19 students. Except for now, we're creating a dress code committee that are composed of 3 students. Using the student names in number 3 above, how many different committees are possible? So in number 3, it made a difference whether you were chosen first, second, or third. So if it mattered what order we were chosen, there would be 5,814 of them. But all of those are not the same, because if we choose a vice president or a president or a treasurer, that's the same committee as if we choose a president and a vice president, and a treasurer. Sorry. So in these, if you're just sitting in a committee together, it doesn't matter the order that you're chosen. So ABC, the same as CBA. Well, in each of these, we've got 3 people. So the question is, if I've got 3 people on a committee, how many different ways could I have done that? Well, how many ways can I make a group of 3? I think I already did that up above. There are 6 ways to make a group of 3. So within these 5,814 choices, 6 of them are going to be identical. And that's like I did up before, ABC versus ACB. So I'm going to divide my 5,614 by 6, and that gives me a total of 969 different committees possible. Sometimes you guys struggle with this division thing, so we're going to talk more about how we can do that without having to figure it out on our own. Number 5 says, how is the answer to number 3 related to the answer to number 4? Well, the way this works is you divide by the number of repeats. So you divide by the number of repeats. And we notice in the ordered group, that was the slate. There are more choices. In the committee group, there are fewer. Okay. All right. So let's move on to number 6. Number 6, we have Bill. Bill has 3 hats, 5 shirts, 10 pairs of pants, and 6 pairs of shoes. He needs to make an outfit. So in his outfit, he's got to have a hat, he's got to have a shirt, he's got to have a pair of pants, and he's got to have a pair of shoes. Not the most attractive shoes, but they'll work. So how many different outfits can he have? Well, this is kind of like choosing the slate of officers. So what we want to look at is how many ways can I do the first thing? How many ways can I choose the hat? Well, there are 3 ways to choose the hat. Then I want to look at how many ways can I choose the shirt? Well, there were 5 shirts, so I'm going to multiply that by 5 because each of those will be a different outfit. How many ways can I choose my pants? Well, there's 10 ways to choose the pants because we have 10 different pairs of pants. And lastly, how many ways can I choose my shoes? I have 6 pairs of shoes, assuming I have to wear a whole pair of shoes. I can't switch them up a bit. I have 6 ways to choose my shoes. So how many outfits are total? 3 times 5 times 10 times 6. I have 900 different outfits that Bill can create from his closet. Number 7, we have Joe's Pizza. Joe's Pizza has the following toppings. They've got pepperoni, sausage, peppers, and onions. All pizzas come with cheese, so that's the default. How many different combinations of toppings are possible? Show all of them or describe them in such a way to show that you have accounted for all different possibilities. Well, the first thing they haven't really specified here is how many toppings are we going to have? We could have no toppings. If we have a no topping pizza, that's just plain cheese. That means we can only make one pizza if we have no toppings. We could have a pizza with one topping. If I'm making a one topping pizza, how many ways can I do that? Well, I'm going to call pepperoni I, I'm going to call sausage S, I'm going to call peppers, I'll call them P, and I'll call onions O. So I could make a pizza that just has pepperoni on it, or that just has sausage, or that just has peppers, or that just has onions. This top pizza, by the way, let me draw him. He had nothing, just cheese. So I can make 4 different pizzas that have one topping. Well, what if I want to make a 2-topping pizzas? Okay, I'm going to have more things here because I can have my pepperoni and sausage, or I can have my pepperoni and peppers, or I can have my pepperoni and onions. Okay, now what if I don't have pepperonis? What if I start with sausage? I could have sausage with pepperoni, or I could have sausage with onions. I'm not going to write down sausage with pepperoni because that was already listed in the beginning as pepperoni and sausage, and it doesn't matter which order I choose my toppings, they're still on the pizza. So I could either choose the pepperoni first, that's what I just did, I chose the sausage first, or what happens if I choose the peppers first? The only topping I have left that'll be different would be to put peppers and onions together. I'm not going to choose onions first ever because I would have to choose a second topping right off of there. So I have 1, 2, 3, 4, 5, 6 2-topping pizzas that I can make. All right, what if I'm going to make a 3-topping pizza? Okay, so if I'm going to make a 3-topping pizza, I could start out and I could do my pepperoni, I could do my sausage, and I could do my peppers. Or I could do my pepperoni, and I could do my sausage, and I could do onions instead. Well, what if I don't put pepperoni on there? What if I start out with sausage, and then I do pepperoni, and then I do onions? Oh, and I got another choice here. I could also have done the pepperoni, skip the sausage, because so far all of my pieces have had sausage on them. So I could do my pepperoni, and then my peppers, and then my onions. So I have 4 toppings, 4 ways that I can make a 3-topping pizza. Last option would be to make a 4-topping pizza. How many different 4-topping pizzas can I make? Well, if I'm going to put all 4 toppings on there, there's only one way I can do that again. So one thing you might notice, I had a hard time, to me, thinking of these 3-topping pizzas, but notice that both of these, the 3-topping and the 1-topping, were the same. What I could really think of for the 3-topping pizza is how many ways can I leave 1 topping off? So leaving 1 off is the same as put 1 on. Put 1 on. So that can help you when you're counting, think, is this the same thing as another situation I've really already done? No toppings and 4 toppings were the same because it's an all or none deal. There was only one way to make it. So overall, how many different pizzas can I make? All of these things put together, 1 plus 4 plus 6 plus 4 plus 1, was a total of 16 different pizzas. Now I also skirted the issue of could I make a double pepperoni pizza, those sorts of things. So you can see I need to be specific when I ask the question of what details I'm going to put in there. All right, we're going to do some more examples of this, but before we do that, I want to go down to do number 8 here. In number 8, it talks about what are called factorials. N factorial, written as n with an exclamation point, is equal to n times n minus 1 times n minus 2, and so on down until we get to 1. Complete the factorial at the right, and then simplify the factorial expressions. So, 1 factorial. 1 factorial is just 1. And On my calculator, that would just be 1. 2 factorial is 2 times 1, which is obviously 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. Eventually, these things are going to get to be a pain to type into the calculator or to figure out in my head, so I want to show you where a button is. On your calculator, if you go under Option, so I hit the Option button on mine. Oops, wait, let me clear this out. If I'm trying to do 5 factorial, I'm going to hit the 5 first, then I'm going to go to Option, which is up here by the Shift key, and then if I hit F6 for more options, and then F3 for probability, so F6 to turn the page, F3 for probability, and you can see there's the exclamation point is F1. So I can do 5, hit F1 to get the factorial, and it tells me that it's 120. By the way, if you have a TI, whenever we hit, here was our Casio, whenever we hit the Option button on our calculator, on your TI, you hit the Math button, and then just like we did, you're going to have to go over until you get to prob, and once you've highlighted prob, you'll see it down in the list, x factorial. Okay, so 6 factorial is 720, 7 factorial is 540, 8 factorial is 40,320. You can see these are starting to get big real quick. Let me fill some of them in before they go off the screen. 720, 5,040, 40,320, 9 factorial, and 10 factorial. Quite big. 362,880, and 3,628,800. Remember, we just did this a lot back at the beginning of the worksheet where we multiplied when we had the presidents and stuff. The president, we had 19 ways to choose them, and 18 ways to choose the next person, and 17 ways to choose the next person. So factorials can help us from typing a long list of multiplications on our calculator. If we're going to simplify, we can either simplify on our calculator, like if I needed to do 5 factorial divided by 3 factorial, I would just want to put it in parentheses, 5 factorial divided by 3 factorial, and you can see that that's 20. An easier way probably to do this for me would be to say, well, 5, that's 5 times 4 times 3 times 2 times 1. That's what 5 factorial is. 3 factorial is 3 times 2 times 1. So I don't really need to put all this in here. I realize I've got a 3, 2, 1 on the top and bottom, so I just have 5 times 4, which is 20. You can go ahead and either try to work these out on your own, or you can put them in your calculator. Just be sure that you're putting parentheses around any top and bottom of a fraction. I'll go ahead and do C with you right now. If you were to do C, you've got 8 factorial divided by, now we know that that bottom is 5 factorial times 3 factorial. I have to put that multiplication symbol in there or my calculator might get confused. And my answer is 56. So you remember when we were taking answers and dividing them by other answers? That's going to start to come up here too. Okay, you can pause the video if you want to try B and C. Okay, so B was 210 and D was 252. All right, hopefully we figured out that we have different situations here, and let's sort of make some generalized notes to describe what we have going on. So you could do this on another piece of paper, or you could just print out the page from the website, whatever you prefer. Counting. For counting, just in general, an example for this, we're going to be something like 7 people are going to march in a parade. Everybody wants to go first, so the order matters. How many different orders are possible? You could pause the video if you wanted to write down this situation. But let's look at, we just did one like this a few minutes ago. If we're going to march in a parade, we have distinct slots, and the order matters. That's important. So we've got 7 ways to choose the first person, then 6, then 5, then 4, then 3, then 2, didn't make enough blanks, then 1. Well, if I don't want to type all of this into my calculator, what could I type in? Just plain old 7 factorial. 7 factorial is 5,040 different ways that I can do this. Okay, so now let's change this situation a little bit. So now I'm going to say there are 20 people who want to be in the parade, but we're only going to choose 7. There's still going to be an order. How many ways are possible? Oops, that should have been a question mark. So now we still have 7 slots, but now I have 20 ways to choose the first one, then 19, then 18, then 17, then 16, then 15, then 14. So what am I doing right here? Well, I would normally be doing 20 factorial on the top if I were going to choose all 20 of them, but I'm only going to choose 7. So I want to take this 20 factorial and I need to divide by 13 factorial. Well, where did I get 13 factorial? That's how many weren't left on the end. If I did this, that would be 20 factorial divided by 13 factorial. Oh, I'm not using my parentheses, but the calculator still understands. That gave me 390,700,800 different ways that I can line up 7 people out of a group of 20. So again, where is this coming from? In this, the order matters. That's what we call permutation. Okay, a permutation in an arrangement where order matters. Okay, so I scrolled down some too here. And the way we do this is it's called NPR. And NPR means out of n objects, we want to select R of them. So the formula for permutations is n factorial over n minus R, the quantity, factorial. And that's what we really just did up here. So in our situation, we had 20 people and we were trying to arrange 7 of them. And our rule said we take 20 on the top, and on the bottom we did 20 minus 7, which is where our 13 came from. So the nice thing about permutations is that you have a button on your calculator that will do them for you. If you want to do a permutation, you type in 20, and then you need the P. If we're already in this option probability section, you see F2 is NPR, and it just puts the P up there, and then you type 7. So that means I have 20 objects. I want to choose 7 of them. How many different ways can I do that? That's what I just had as my answer before. So again, in a permutation, the order matters, and that's the key for this one. All right. Now, what if we just said, instead, there are 20 people in the class, and we want to choose 7 of them to be on a committee? Okay, again, you can pause the video if you want to write this down. But if we're trying to figure out how many committees are possible, in this one, it's a big distinction because the order doesn't matter. Huge distinction here. So if the order doesn't matter, we're going to have a lot fewer choices because we have repeats. If I chose ABC, that was the same as choosing CBA, so I can't count that as a different committee. So I know I'm going to start with the same type of idea, except for now I'm going to call it 20 choose 7, and it's the other button, the combination button, and we'll look at what this does in just a second. But I'd hit 20 and then the NCR button. 7 to do a combination, and you see I get a much smaller answer. Well, where did this answer come from? Just like I did with permutations, I would start with my 20 ways on the top, and then I had to divide by the 20 minus 7 on sorry, I had 20 factorial on top. I divided by the 20 minus 7 factorial on the bottom, just like I did, and that would give me so far the number of permutations. Now I have to get rid of all the repeats. Well, how many repeats are there? There are 7 factorial ways to arrange the 7 people on the committee, so I also have to divide by 7 factorial, and that's where this number comes from. You can see if I had typed it into the calculator this way instead, 20 factorial, 20 factorial divided by, I'm just going to type 13 factorial because it's easier than doing the subtraction, times 7 factorial, and that's the same answer I got before. So this is called a combination. Combination, just like I said, the order does not matter. We write it just like we did the permutations, except for it's NCR. By the way, we can also write this with a parenthesis, and we can stack the N and R like you would in a fraction, just no fraction bar in between. So that's 2 different notations for writing NCR. And we start with the N factorial on the top. That was the big number on the top. Then again, we subtracted them just like we did for the permutations on the bottom, but we also divided the bottom by R. You could see it written this way, or you might also see this written as N factorial over R factorial times N minus R factorial. Doesn't matter how you write it, and if you look at the Algebra 2 formula sheet, the permutation formula and the combination formula are on there, but honestly, it's just easier to use the calculator button in the first place. So in the future, if you're reading a word problem and you're trying to decide if it's just a straight up counting problem, you could multiply the number of items for each choice together, or you could think of it like a permutation if the order matters, or you could think of it like a combination if the order does not matter. So you're going to have to look at things to decide order matters if you're making a seating chart, order matters if you're winning a race, order matters if you're electing people for specific offices. Order doesn't matter if you're doing something like choosing people to be on a committee, if you're choosing items to dump into a salad and mix them together. In those kinds of things would be combination when the order doesn't matter. All right, you could do the permutations and combinations activities, and we can look at examples from these in class if you have any questions. Thanks.